Many of the reactions we're going to talk about in this course actually take place while the reactants and products are surrounded and embedded in a water environment. So we're going to be interested in knowing how to think about these reactions in solution, and that's the subject of this video. So what are our learning goals? Well, we want to know how a chemical reaction may appear on an atomic scale, what conditions are needed for those atoms and molecules to actually have a chemical reaction, and what effect the solution environment may have on chemical reactions as they take place. What is actually going on in a solution? Let's start by thinking about the necessary conditions for a reaction to take place. What do we need to have happen? Well, I think first and foremost, the molecules that are reacting have to collide with one another. They have to come close enough so that something can happen with their valence electrons to lead to a new stable state. And usually this can only happen if the two molecules collide, or three molecules, but there has to be a collision of some kind. It's also true that they must have sufficient energy. We're going to see that many reactions require some energy in order for the reaction to take place, and a lot of times that energy comes from the collision itself. They must also be oriented properly. If two molecules come together, they don't necessarily react if they're not oriented in the right way. So if they hit each other the wrong way, they may just bounce off of one another. Now, to remember these three factors, I'm going to introduce you to this acronym. It's one that you're probably familiar with in another context, but the C here stands for collision, the E for energy, and the O for orientation. For a reaction to take place, you must have all three of these really working in tandem with one another to make it happen. Now, I also have an analogy to help you understand this, and that is a hammer hitting a nail. If you want to drive a nail into a board, you probably will use a hammer, but you know that if you don't hit the nail with the hammer, you'll never drive the nail into the board. So there has to be a collision. Now, if you had the hammer turned the other way around so that the tail end of the hammer was hitting the nail, you probably wouldn't drive the nail very effectively. So you need to have them oriented properly too. If you don't hit the nail hard enough, you won't drive the nail into the board either. So you have to have enough energy. So you have to have all three things. You have to have a collision, you have to have enough force in your hammer blow, and you have to have the hammer oriented correctly in order for it to drive a nail into a board. Now, when we talk about collisions, we want to think hard about how frequently do molecules actually collide. Is it possible that they don't collide very much at all, or they collide all the time? Well, it turns out that the more molecules we have in a given volume, the more often they will collide. I think that makes sense. So if I drew a picture here and just show two molecules in this small box, it doesn't look like those two molecules are going to collide very often, just because, for both of them to be at the same place at the same time, it's just not likely to happen. So what would I do to increase the probability that a collision would take place? Well, I could introduce more molecules to that same box. I could also make the box smaller. So both of these things will lead to more frequent collisions, and so it's more likely to support the possibility of a reaction happening when we can do these things. We'll see that these are particularly useful when we're talking about gas phase reactions, because we can manipulate the volume of a gas and cause more molecules to have collisions. Then we can also increase the number of molecules colliding, and that can happen either in a gas phase or a solution phase. So the key here is we're going to talk about something called concentration, which really is a way of measuring the number of particles or molecules. I put a slash between them to say it could be either one. But how many there are of those for per unit volume? So we want to know how concentrated our reactants are going to be in our reaction vessel. Now, let's get on to solutions. What is a solution? I've given you a definition here. It's basically a homogeneous mixture. What does that mean, homogeneous mixture? Okay, well, mixture I think we can figure out. It's more than one thing is together in there. Homogeneous means that you can't tell it's a mixture. In other words, it's such a smooth blend of the things that are in the mixture that you can't tell it actually is a mixture when you look at it. Now, I want to define a couple of components in a mixture. First of all, the solvent is the major component. Usually it's a liquid. In most of the reactions we'll talk about in this course, that solvent is going to be water, although in the organic chemistry lab you use a whole bunch of different solvents, and there are other solvents that are also known in the environment. But water is going to be the main one for us. The solute is the thing that is dissolved in the water. So we want to be sure that we understand the difference between a solute and a solvent. So, for example, I could mix water and ethanol, and those mix together pretty well. In fact, most liquors that you might buy in a liquor store are mixtures of water and ethanol. They actually have a fairly small percentage of ethanol, believe it or not, but they are homogeneous solutions because you cannot tell that there's those two things in there. But if I tried to mix water and oil, that forms a very inhomogeneous mixture. The water and the oil do not blend together very well. In fact, they separate, and oil tends to, I guess, move to the top of the water, and the water is below. Now, if I wanted to look at an atomic scale or a molecular scale, a solution might look something like this. Now, this obviously is a cartoon, so this isn't really what a solution looks like. But I've drawn the solvent molecules as blue circles and the solute molecules as red circles in this. Now, what I want you to notice from this diagram is that there are many, many more solvent molecules than solute molecules. This is typical for a solution. I also want you to notice that each of the solute molecules, the red circles, are surrounded by solvent molecules. In other words, they are completely entrapped by a group of solvent molecules. We call this a solvated complex. It's a way of saying that each of the solutes is going to be completely surrounded by solvent, and that's one reason that it's homogeneous. It's one reason we can't tell it's a mixture, because in fact, to other water molecules that are not involved in that solvation effect, to them, that solvated solute molecule simply looks like more water. So the basic picture is this one. And so I want you to think about solute molecules, especially if they're reactant molecules, being engaged in this sort of environment and what that means for their ability to get together and react. So let's talk about reactions in solution. Now, I'm going to use an analogy to talk about this, a party analogy. I know that in this day and age with coronavirus raging around us, we don't have many parties anymore, but I hope you still remember what parties were like, and hopefully someday we'll get back to them. So in a reaction in solution, reactant molecules are surrounded by solvent molecules, and they have to diffuse through the solution. That just means they move through the solution. So our party analogy is that R and J stand for Romeo and Juliet. R and J spot each other across a crowded party floor. Okay, so Romeo and Juliet getting together here. The two solvation shells that surround those reactant molecules have to merge. So this is Romeo and Juliet approaching each other, or maybe across the dance floor, or certainly across the party venue. The molecules experience a long collision. Okay, this is a slow dance. They're colliding over a long period of time. The energy is provided to those molecules by the solvent environment. Now, so this is, went from a slow dance to a fast dance, but one way or another, energy is imparted to those molecules that are going to react by the solvent molecules that are around them. So there's lots of collisions going on, so it's not that each one delivers a lot of energy, but it's the cumulative energy that they all deliver to that reacting pair. The reaction occurs. Of course, in our analogy, that would be they exchange their cell numbers. You can think of other things they might do. And finally, they will diffuse away from each other. The molecules will diffuse away from each other as products now in the solvent. So this is how molecules get together and react within a solution phase. And so all of the reactions in solution that we talk about will follow this general set of steps. I don't have a final step for the party, but you can use your imagination.